All right, so let's talk some more about those derivatives, okay? So here's an example graph. It says, suppose an eccentric pet ant is constrained to move in one dimension. The graph of his displacement as a function of time is shown below. Okay, so at time t, the ant is located at point A. While there, its position coordinate is x. At time t plus delta t, so at this new time right here, the ant is located at point B. While there, its position coordinate is x at the t plus the delta t. All right. So if you were in AP1 last year, we did some of this where we looked at the slope of this line and we saw that that was equal to a point, the midpoint of that time interval. A line, I should say, the slope of this line was tangent to the slope of a line that was tangent at the midpoint of this line. Okay, so we could get the slope here. And we do that the regular way we do slope, rise over run. So that's the equation they show down here, okay? The tangent lines are what we did last year, okay? So if we hold a point A fixed while allowing delta t, or the change in time, to become very small, point B approaches point A, okay? So basically, if we were shrinking this time interval down, that point would be getting closer to A, okay? So what that means is that secant line we drew a minute ago approaches this tangent to the curve at point A, okay? So this red line is your tangent line. We did some of that last year, okay? Basically, what this is allowing us to do is zooming in, okay, at a point where a line appears straight. So basically, they took these A and B and kind of shrunk them together to get this tangent line here, okay? So mathematically, we just found the slope, all right? You had to take the slope of the secant line, then you had to look at the slope of the tangent line, which turns out to be exactly the same, okay? Don't worry about the limits right now, but that's what the LIM here stands for. That's the limit, and it shows as the change in time approaches 0, okay? As this happens, the top part approaches a finite number, okay? So a specific number instead of a range if we were looking at the slopes of all of the points on that curve, okay? That's what a derivative is. A derivative gives you a new function that defines the rate of change of the original function with respect to one of its variables, okay? So earlier I said the average velocity is the derivative of velocity with respect to time. That's what it's talking about right here, okay? The average acceleration, or sorry, it was the instantaneous acceleration was the derivative of velocity with respect to time. When I talked about velocity, it should have been instantaneous velocity. All right, in most physics books, the derivative is written like this. So the derivative of position with respect to time, this would be for an instantaneous velocity, okay? This is treated as a single symbol, which means find the derivative, okay? It's just a simple mathematic operation, okay? So basically the bottom line that you need to know is the derivative is the slope of the line tangent to a point on a curve, okay? So here's an example of a derivative. So if you're looking at this function right here, the position as a function of time is equal to 3 times the time plus 2, okay? So what is the time rate of change of the function? Well, that's what we're looking for. The new function that defines how this changes, okay? So this is really, really easy. The entire equation here is linear. It is set up as y equals mx plus b. Thus, we know from the beginning that the slope, the derivative of this, is equal to 3, okay? Because that's our slope right here, y equals mx plus b. But let's look at how we do this with calculus, okay? So here's my original equation. Then the derivative of x with the respective time. Don't worry about all this stuff. We're going to look at it over here. What we end up with is 3 times the change in time divided by the change in time is 3, okay? So let's look at I'm not going to go through a bunch more of these. I'm going to show you some examples where it looks a little bit easier. But basically, here's another function. They take you through all these mathematical steps. You do not have to write all these mathematical steps for physics.